we were looking at a type of function where you feed it a point and the range or the output is a real number. So we're continuing to do that right now. So we did some evaluating of a function of two variables here in example 1. And in example 2, we're going to find domains. Now, the domain guidelines that I went over in massive detail for vector valued functions still apply here, but it's a little bit different level. Instead of just a single variable like the vector valued functions, just time t, so you had intervals, we're not doing intervals now. We're doing the entire xy coordinate plane. So if you look at the entire xy coordinate plane here in 3D, it's this right here. Points that live in the xy plane are going to be the elements of the domain, of the input to a function of two variables. Now the question is, can the function eat any point that lives in this xy coordinate plane? Now you can start off, this is how I do. I assume that the function can eat anything. He could eat any of these points that live in the xy coordinate plane. Only if there's issues do I start eliminating points from the xy coordinate plane. So what are the points that I would eliminate based on my knowledge of finding domains of functions from pre-calc as well as vector valued functions? So if you look here, I have an x in the denominator. Ooh, we do not like denominators equaling 0. That would be bad. So that's going to be one item that we're going to take away. Now x is 0 on the entire y-axis. So what we're doing is we're basically saying the y-axis is off limits. And you're not allowed to feed values that are points rather that live on the y-axis to this function because he'll die. Okay, now are there any other points that he's not allowed to eat? Well, look, we've got an even radical, and we don't like taking square roots of negative numbers. Square root of 0 is okay, that's just 0. Square root of a positive is okay, but square root of a negative gets us into the world of complex numbers, and we avoid that in this class. So we want the radicand x squared plus y squared minus 9 to be greater than or equal to 0. Now you can leave it like that, but a lot of times it's nice to kind of rearrange this inequality. I'm going to add 9 to both sides, and they're basically saying x squared plus y squared greater than or equal to 9. Now let's talk about how you would write your answer. You can't do intervals or interval notation like you did for vector valued functions where you'd intersect all the sets. Instead, you're going to use set notation for all domains of functions of more than one variable. So that means you're going to have curly braces like this. So I want to see the curly braces, although you're writing on my math lab. And then you say all generic ordered pairs, so the points look like x, y. And then I like to put a vertical bar here. It basically you're saying all the ordered pairs x, y such that some books and some, and I'm not sure, I don't remember what my math lab does, sometimes they'll put a colon there instead. Either way, it means the same thing. So you may see a bar or you may see a colon. It basically means all the points such that, and then you put in the issues. So the issues we have, and you just delimit the issues by commas. Here we have two issues. Our denominator, we don't want it to be equal to 0, comma, and we need x squared plus y squared greater than or equal to 9. I'm done, and this is the final answer in set notation. Now, let's go down to the sketch below here. If I had to shade in the okay points in the xy plane, this is the xy plane, what would I shade in? Well, x squared plus y squared equals 9 is a circle centered at the origin of radius 3. So you'll see here that this circle of radius 3 centered at the origin, and notice because that originally was a greater than or equal sign, you put a solid line for the border of the circle, but then you want points that are greater than or equal to. So that's going to end up being points that live outside of your circle. So you're going to shade in points outside the circle, including the boundary of the circle he's allowed to eat. But remember that x not equal to 0. So You want to put a fence, and you'll notice that they did it for you. There's sort of a dotted line on the y-axis, although it's really hard to see with this diagram. That's one way to show that we're not allowed to eat any points on the y-axis. The way I like to do it is, I like to put that border here around my circle, and right when I get to the y-axis, I put a little fence here, which shows me I'm not allowed to eat any of the points that live on the y-axis. And so this, now I'm done. I just shaded in all of the OK inputs to the function described in part A. That would be all of his domain. And you care very much about this, because when you would sketch the surface, which is a graph of the function of two variables, because the surface is in 3D, the surface is only going to hover, you know, because you can think of the z-axis as sticking straight out of this paper. The surface points are only going to hover over the shaded portion of the xy coordinate plane. So there's no surface that would be hovering over, say, this middle part where inside of that circle, because those are not OK points to feed the function, not in the domain. Okay, let's do letter B. It's harder. So what about this one? You got all this different problems and issues. So let's address the issues one by one. First off, we don't want this term's denominator to equal 0. So 4y squared minus 2 not equal to 0. So that's one issue. And you could write it like that, or you might see it written where they add 2 to both sides. So 4y squared not equal to 2. Either way is fine. And then the logarithm, ooh, you care about logarithms because you don't want to take ln of 0, that's undefined. And you certainly don't want to take ln of a negative number. That ends up in the complex number world. So you want the argument to be strictly greater than 0. And you could leave it like that, or if you want to get cute, you can add the x and y terms to both sides of the inequality, and you're basically saying that x plus y has to be less than 2. Fine. Then what? Ooh, we have another even radical. Oh, holy moly. We need the radicand to be greater than or equal to 0. Or you could write it like this, x to the 4th greater than or equal to y to the 4th. If you add y to the 4th to both sides, that's fine. And then sine of xy has no restrictions because you don't care what the domain is for sine. He's allowed to eat any real number. So now how do you put it all together for part B, since I've ran out of room? So the answer to part B, let's append a page. You want to use set notation. And so the answer to part B is going to look like big old set, woo, leave lots of room, all ordered pairs x, y, such that, and then just start putting in all your issues, okay? Now I do want to say that in my notes I have something a little different. For this one I went a little bit extra. I divided both sides by 4, and then I took the square root of both sides of an equation. And what do you have to remember when you square root both sides of an equation? Does anybody remember?
Plus or minus.
Very good. So we need, so what we're saying here is y not equal to plus or minus 1 over square root of 2. That's how I wrote it in my notes. But you could have left it the original way, but this is kind of like a little bit more clear of what we're restricting the domain here. And then we had the x plus y strictly less than 2, and then we had x to the 4th greater than or equal to y to the 4th. And we're done. So those are all the 3 issues for this domain, and you just delimit them by commas. And that's the answer for letter B, and we're done. So letter C is a little bit trickier because you have a function of 3 variables. Now, folks, a function of 2 variables, you can graph it. So because you need 3 dimensions to graph, and it's a surface. If you have a function of 3 or more variables, you cannot visualize the graph. You cannot. But you can still talk about functions of 3 or more variables. You don't have to visualize a graph. And please don't come up to me after class and go, yeah, there's a thing as such as 4 dimensions and woo, you know, whatever. Like time, you know, time is the 4th dimension. And it's going to be like, yeah, I get that, but it's still not that time dimension. It can't be graphed. Like you can't visualize what that's going to look like. Look, physicists, when they talk about all their, you know, weird theories like, you know, multi-universes and string theory, I was reading this book written by a mathematical physicist, Roger Penrose, not too long ago, and he was trying to visualize 6 dimensions and how physicists were visualizing 6 dimensions. And so he had a diagram, and it was complete BS. You know, he even admitted, yeah, you can't. Yeah, this is sort of a weird diagram just to kind of help you get your mind around the 6 dimensions I'm talking about. And it was like, yeah, right. You can't do it, but you can certainly talk about it. And we will talk about it. So but here what you assume that he could eat any ordered triple in space, because that would be his domain, ordered triples, you know, points in 3D, and then his range would be some value corresponding to that ordered triple, like a temperature or something. And it turns out we have to worry about 2 things for letter C. So what do we have to worry about? First, you want to make sure that your radicand is definitely greater than or equal to 0. But because the radicand is in the denominator, you don't want it to be equal to 0, so you have to change this to a strictly greater than because it's in the denominator. So your final answer, set notation, is going to be all ordered triples, x, y, z in parentheses, all the points that live in space, such that, and then you're going to put, you can either put this inequality that we have here. I'm going to add x squared plus y, and the y squared and the z squared to both sides of the inequality. And then I'm going to flip it around just so you can get, because it means the same thing as x squared plus y squared plus z squared less than 9. And we're done. And that is the domain for that function of 3 variables. Now, what if I had to graph that? You can actually graph his domain. You can't graph the actual function, but you can graph his domain because that's in 3D. So I hope that everybody in the room would be able to graph this equation if this were an equals. If this were an equals, what would this graph look like for this equation? I'll open it up and see if anybody...
Is that a sphere?
Yes, thank you. Centered at the origin of radius 3, right? So, well, I'm having some problems with my Surface Pro here. I don't know. Nope. Okay, come on, guy. What you doing? So you have a sphere centered at the origin of radius 3, but I'm going to draw it with a dashed border. That's a terrible looking sphere. Why am I drawing it with a dashed border? And I can shade everything inside the sphere. Why is there a dashed boundary?
Those values aren't included.
Correct. Because this is a strictly less than symbol, any ordered triple that lives on the actual boundary of the sphere and not actually inside would be forbidden as part of the domain of this function of 3 variables. Very good, Alec, very good. Okay, so there you go. That is domains. Now let's talk about more about graphs. Okay, let's stick to graphs of functions of 2 variables because you need 3D to graph a function of 2 variables, and you're going to end up with surfaces, which we're going to study for the rest of this semester. So let's talk about how they come up with this. So the graph of a function of 2 variables is a set of all ordered triples for which z is equal to f of xy. So xy is in the domain. So you're going to feed it a point here, and then it's going to poop out a z coordinate. And the z coordinate gives you the altitude or the height. Altitude. So that's how high you are above your point, or it might be a negative, so then you'd be below. Okay, so then you just collect all of those heights, and then you kind of connect them all together, and you get your surface. And this particular surface, you'll notice, is hovering over the domain, because only the points that live in the domain down here that's shaded in are permitted to be fed to your function. So there's your surface. It's kind of restricted. And we can talk about passing the vertical line test, just like you did when you took algebra and pre-calc and calculus. This capping surface, I like to call this a capping surface because Dr. Vallone, may he rest in peace, my mentor from San Diego State, he used to call those kinds of surfaces that look like a cap. That's a capping surface. That passes the vertical line test because you could run a vertical line through it and move it anywhere around, and it only intersects the surface at most once. But this ellipsoid, even though it is a beautiful surface, you know, it looks like an egg, and you guys studied ellipsoids in 13.6 for quadric surfaces, is gorgeous. But it doesn't pass the vertical line test, because when you have a vertical line here, it intersects the vertical line more than once. So it intersects twice. So it definitely doesn't pass the vertical line test, but it's still a surface. Okay, now if you can write your equation in explicit form, so explicit form is z equals f of xy, so where you could get the z isolated on one side and all the rest of the junk on the other, that's called explicit form. If you can do that, you're guaranteed that your surface passes the vertical line test. Why? Well, check out this elliptic paraboloid. I claim the equation for this puppy is fxy equals x squared plus y squared. And just like when you were in algebra, if you recall in algebra that if you had f of x, for example, equal x squared, you can write, or you can replace f of x with y. Remember this? Please say yes, because you're going to have a similar analogous thing happen to us here in Calculus 3. If somebody writes f of xy equals whatever, stuff that has x's and y's in it, you can rewrite or replace f of xy with a z. They mean the same thing. These two equations are what we call equivalent. Which is better? They're both the same. Now sometimes you're going to want the z equals x squared plus y squared format, because you're going to have to get it into what we call implicit format. So this paraboloid is passing the vertical line test, and we can write it in explicit form where we isolate the z on one side. Ellipsoids aren't as good, because if you recall, like I can have an ellipsoid, say that x squared over 2 plus y squared over 3 plus z squared over 4 equals 1. There's an ellipsoid equation. You can solve this for z, certainly. But when you take the square root of both sides of an equation while you're trying to solve for z, what are you going to get? I'll leave it open. What happens when you take
Plus or minus?
Yeah, you'll get plus or minus, you know, the 1 minus, you know, you'll have probably a 4 out there too. 1 minus x squared over 2 plus y squared over 3, or minus y squared over 3. So you're going to actually have to graph two things. The plus will give you the upper half of the ellipsoid, and the negative square root will give you the lower bottom, or the underbelly of your egg. So you need two different equations there. So that kind of gives you a heads up that it's not passing the vertical line test. Okay, so I'm done talking about graphs. Let's do a little bit more when we talk about range. When you found a range in an algebra class or a pre-calc class, you were finding the y values that get hit. But now you're going to be interested in finding the z coordinates that get hit. So what z coordinates get hit with this function? Well, you notice that this function, you need the radicand to be, so the domain would be the set of all points where the radicand was greater than or equal to 0. So you're kind of limited in what you could feed this particular function. And that happens to be an ellipse in the xy plane. So if you rewrite this inequality where you set it equal, it's going to end up being all the points on or inside the ellipse given by, and I'm not going to do all the thing, I'll just kind of quickly do this. And then if you rewrite this in standard form by dividing both sides by 16, you'll get the standard equation for an ellipse like that, okay? Now the range is going to be the highest that the z gets and the lowest that it gets. And because this is a square root function, the lowest value a square root can hit is square root of 0, which is 0. And the highest it can get, since you're taking 16 and you're subtracting positive numbers from it, the highest it can get is square root of 16. Or basically, your range looks like all values z that lie between 0 and 4, inclusive. So if you look at a picture of this graph, so point xyz is on the graph if and only z looks like this. So if you're not clear about, well, what does this graph even look like, you can square both sides to kind of get you back to the quadric format. And then you'll notice that after adding the x squared and y squared terms to both sides, this is an ellipsoid. But it's not the full ellipsoid, because when they solved for z, they only took the positive portion. So it's only going to be the upper half of an ellipsoid. So you can see that the highest it gets is 4, the altitude that is, and the lowest it gets is 0 when it's in the XY plane. Okay, so I don't usually ask you for range on quizzes and exams because sometimes it can be rather difficult because that means you have to graph everything in 3D and it's hard. So full disclosure, don't worry too much about range. I do want you to worry about domains, though, because that's just following a set of rules, and it's pretty easy. Put it all together with set notation. Okay, I've been talking a lot. I'm going to take a quick break, look in the chat, see if anybody has a question or two about what I just covered before we go into.
Can you scroll back up a little bit for the notes?
Okay,
Thank
tell
you.
me when.
That's good.
Okay,
That's perfect.
all right, anybody else?
Why was z less than or equal to 4 in that example?
Why is that the case?
Yes.
Okay, so look at the original equation right here, George. Can you see my screen okay?
Yes.
Okay, now let's think about that square root. You 16 minus some junk.
Hmm?
And you notice, I'm going to have to put you guys on mute. Okay. So if you'll notice, George, that you're taking the 16 and you're subtracting some items that are actually positive numbers because of the x squared and the y squared. Is that understood?
Yeah.
So if you're taking 16, but then you're taking away from the 16, won't that lower what the value of the square root is when you start taking stuff away from the 16?
I'm sorry, can you repeat that again?
Okay,
That statement?
how about if you look at my screen? Let's say what's the square root of 16 equal to, George?
4.
Thank you. What's the square root of 16 minus 1 minus 2 equal to, George?
16 minus 1. That's the square root of 13.
Yeah, but isn't the square root of 13 a number less than 4?
Yes.
Okay, what if I had square root of 16 minus, 7 minus 3? Or how about I'll do 7 minus, this, how about, let's do this, how about minus 3 minus 4?
It'd be the 3.
Okay, but
Square
isn't
root.
that a number less than 4?
Yeah.
Okay, what I want you to get, and I don't know if you're going to buy it yet, but I sure hope you will. I'm hoping you're going to buy this. That the highest value that this square root can attain is the square root of 16. Because any other values that you put in there for x and y that aren't where x and y are both 0 will decrease the value of this square root. It won't be as high as the 4. Is that clear?
Okay, and then it would no longer lie in the domain because then
No, it's
it would
going to
be
lie
less.
in the domain. It's going to, like 16 minus 3 minus 4, that's in the domain because you can take the square root of positive 9. That's
Yeah,
cool.
but like I'm saying, if it goes, because if the
Well, yeah, if you let x be 10 and y be 57, you're going to get square root of a negative number. And this point, the point with coordinates 10, 57, I hope you get that point does not lie in the this ellipse here in the xy plane, because that's when you graph the domain of this function, which we talk about up here, right here, the point 1057 is not in that neighborhood.
Okay.
Does that help?
Yes, thank you.
Okay, so the highest that this guy can get is a 4. And I hope you can even buy it further by looking at the graph, can you? I don't
Yes.
know. I hope. Okay, any other questions?
Can you go back a little bit to the top of this page? Right there.
Mm-hmm. So the next topic I'd like to visit is called level curves. So for those of you who are really into topographic maps, this will be kind of easy for you to grasp. If not, we'll try to go from there. But the idea of level curves is very important, and then we'll finish off by doing level surfaces, and then hopefully we'll have time to do limits today. That would be my goal, but we'll see how far we can get. So one of the announcements, now that I think most everybody is here, that I wanted to talk about is next Monday there will be no class, okay? I have a Jewish holiday, but that doesn't mean you're free and clear to do anything you want. You still have a quiz due that morning at 8:30 a.m., so please be mindful of that, and you got to upload your work, okay? It's got to be uploaded by 8:30 a.m. And the other thing is, if I don't finish getting through partial derivatives, you're still responsible for watching a whole bunch of videos on partial derivatives that I spent a good portion of my summer creating for you, and I even got them closed captioned. So what am I talking about? You have to watch these, and they go with the course reader. So remember I asked earlier, for those of you who are kind of unhappy with your scores, are you willing to go to any length if you're going to stay in the class? Well, are you? I don't know. So here in week 6, well, I'll open it up. I have 1, 2, 3, 4, 5 videos that are in order, and they go over the section, which I believe is section 13.3, on partial derivatives. I basically lecture to you. That I try to keep them relatively short. That's why I broke it up into 5 instead of just making one big old 2-hour lecture, you know. So you're going to go in here, you know, click in here, and then you're going to, and it's got closed caption and everything, so it's got a little smart player, so you can go ahead and with your course reader take notes as I do it. And if you know, you can rewind it or do whatever you want there, which is really helpful for you. Okay, so that's your job. To do that on Monday, because if I run out of time and don't have time to hit it on Friday, that's on you, because we're very jammed for time, and we have to hurry. That's why I don't ever take time to go over solution keys and so on. We just don't have time. You got to cover a lot of material in this course. It's a nightmare, and that's how we roll. So you're going to have 5 of those to go look at. So next Monday, as a reminder, I do not have any class. You don't have to Zoom, so please don't show up in Zoom and go, hey, how come there's no Zoom today? What the hey? And the answer is because there is no Zoom on Monday. Okay, all right, level curves. Have you guys ever seen one of these puppies, this contour map? Do you know even how to read one?
I've seen it, but never known how to read one.
Okay, let's talk about it. Do you see all these weird squiggly lines all over the place?
Yes.
If the squiggly lines are super close to each other, so if there's the closely spaced contours, like this area here looks like the squiggle lines are very close to each other, whereas over here they're kind of widely spaced. They're not as close. So if you're near where the squiggles get closer and closer and closer, that means that the elevation is changing very rapidly, probably a very mountainous range. Ooh, they have the word mountain there. Ooh, there's a surprise. Ha ha. Yeah, but when the squiggle lines are kind of far away from each other, those are the level curves, that means you have very slow, gradual changes in the elevation, you know. So if you're going to do some hiking and you're not very physically fit, you might want to choose this area here where the elevation changes quite slowly. On the other hand, if you like, you know, to get your butt kicked and do a serious hike with, you know, lots of hills and mountains, then you want to go over here. Okay, so that's sort of the idea. And how do you draw one of these contour maps? I'm going to go over that. And yes, you have to. Now, in my math lab, they usually give you multiple choice level curve pictures, so they don't actually make you graph them. But I'm going to go over how you would graph them by hand so that you have an idea, so that you pick the right one. Okay? So a contour map, what it's doing here is, like, if you're in an airplane here and you're looking down at the mountain, so when you're looking down, you're going to see, you know, rings or these curves, which might be squiggles. Those are your level curves. That's, you know, taken together, it's known as a contour map. So if you have, if you'll notice this mountain here, it looks like these rings here are going to be the level curves, and sure enough, this guy has the contour map looking like that. Now, if you were hiking, let's say you were hiking on this mountain and you didn't want to go up, you wanted to stay at the same level. Well, then you would stay on this level curve, which looks like a ring here. You would just, go make a ring around the rosy there, ring around the mountain, and that would keep you at the same elevation. So that's a good thing to think of. The word level and the level curves, that's a key word for you because it means you're staying at the same level, the same altitude. Anytime you move off of your level curve, you're going to either increase your elevation or decrease your elevation depending on what the surface is doing, the mountain is doing, okay? So in this case, if you move upwards, higher up the mountain, you jump off your level curve or your contour curve, you're going to get a higher elevation. If you go down, you'll get a lower one. So here's some other examples of level curves. Check out this thing. It kind of looks like two, I don't know what that, it looks like two volcanoes right next to each other. I don't know. Somebody did a contour map for those two guys. So that's what it would look like. Okay. This is a contour map for something else. They're not showing you the surface that would go with. I think it would probably be a hyperbolic paraboloid or something. Let's take a look at this next example here. So how would we come up with a contour map for this hemisphere? This is actually pretty easy, so watch closely how they come up with the level curves. The first step, and this is what I always want to see on your paper, is you set the function f of xy equal to a constant, some scalar. It doesn't matter what the scalar is at the moment, but start off with setting it equal to a constant. So then, in place of the function, this function is the square root of 64 minus x squared minus y squared. Set that equal to a constant. And then square both sides, because you're just trying to get it. What's the goal here? Well, you're trying to get the equation to look like something that you recognize from a pre-calc class or maybe an algebra class. And if you can't recognize it, you're screwed. Like, you're not going to be able to figure out how to go from there. And don't guess. Although a lot of people do guess on my math lab and they get the right answer. And you'll notice when I grade your papers, guessing is typically not good enough for me. I want to see, a legitimate mathematical argument about how you got an answer. It's not so much in this class, Calc 3, because it's a little harder to snow me, but are you guys still there?
Yes.
Okay.
Yes.
Got real quiet all of a sudden.
Yes.
Okay, thank you. So in my Calc 2, they also had a midterm Monday, and woo boy, I don't know what to tell you other than there's a lot of unprepared Calculus 2 students out there, and they did a lot of snowing. Like, as an example, on their handwritten work, I would give them an integral that would be a definite integral because they're learning how to integrate. And they would just write down the integral, the definite integral that they're supposed to do the work on, and then equals the answer. Well, thanks for that. Thanks for the tip. No work shown at all. Just boom, there's the answer. Wow, that's incredible. And 0 points for that. Now, my math app gave them full ish, but I go in there and put a 0 in there. And then I write down on their paper, please show work. So that's going to happen to you if you do the same. So then what? Well, this equation, if you kind of move it around a little bit, like, well, how? Like, suppose I subtract c squared from both sides, that's just a number, and add the x squared and y squared terms to the other side. Does this look like something that you might recognize? And I claim, yes, it does. It looks like circles. C, you can pick different numbers for c. So let's let c equal 0, and let's examine the level curve that we would get. Oh, that's just a curve that's a circle centered at the origin of radius 8. Okay, fine. And then you would let c equal some other number, like c equal, I don't know, whatever. You usually want to pick your c's that are evenly spaced from each other. So you would then maybe select c equal 4, and then maybe, well, I maybe do something like this, maybe c equals 2, and then c equals 4, or you could pick 1, 2, 3, 4, 5, 6, 7, 8. Either way, if you did pick, say, c equals 2, then you'd have 64 minus 2 squared, which is 60. So your level curve would be x squared plus y squared equals 60. So then you'd also get a circle centered at the origin, but the radius would be whatever the square root of 60 is, right? Which is a number less than 8. So then you would get some other circle. And you would keep going, and then you would just get a bunch of concentric circles, similar to the way what you see those rings there, but flattened onto the XY plane. So we're pretty much done with that problem. And the idea is set your function equal to a constant, rearrange it, rewrite it so you can recognize it, you know, whether circles or maybe they're parabolas or maybe they're ellipses, who knows, some sort of equation that's recognizable, and then start plugging in various values of C and actually graph those equations, and that'll give you the contour map. So what about this one? This one's a little weird. If you looked at this surface here, just to let you know, that's a hyperbolic paraboloid is one of the quadric surfaces, and if I graphed this one, I think it would look like a horse's saddle. It has this sort of look to it. You know, here I'll draw a horse. There we go. Okay, there's a horse. So this surface here, which is a hyperbolic paraboloid, looks like a saddle. What would the contour map look like for that surface? So don't guess, you know, go through the analysis here. So step one is you set the function, whatever he is, equal to some constant, okay? All right, well, what's y squared minus x squared equal to some constant? And now you don't even have to really do a rewrite. What the heck is that? And it turns out that this is a hyperbola. And I hope you remember from your pre-calc days the equation for a hyperbola. This happens to be an up-down hyperbola if C is positive. So if C is something positive, you'll get, and then I'll let C be, you know, 1, 2, 3, whatever. If you let C equal 1, the hyperbola, it's an up-down hyperbola, looks something like this. If you let C equal 2, you know, C equal 3, whatever. If you let C be, so these are what we call vertical hyperbolas. If you let C be negative, like let's say C equals -1, so you get y squared minus x squared equals -1. Well, the hyperbola standard equation, you always want a +1 on the right side. So you would multiply both sides of this equation by -1, and then you would have minus y squared plus x squared equals 1. These are what we call horizontal hyperbolas. So then you would get another collection of hyperbolas. This is going to all add into the mix because you're basically getting a full-blown contour map here. Oops. And so there you go. It's kind of a mess. I didn't actually plug in values of C, but you would, and then you would get this big old mess, which is vertical and horizontal hyperbolas, and boom, there's the contour map. Okay, I'm done talking about level curves. Let's jack it up a notch. Let's talk level surfaces. What is a level surface? If you're given a function of 3 variables, so you start, this is for functions of 3 variables. You cannot graph this. Let me stress this. You cannot graph a function of 3 variables because you would need 4 dimensions. And we don't really have that visualizing capability. That doesn't mean that mathematicians don't talk about 4-dimensional space. They do. They talk about 5-dimensional, 10-dimensional, n-dimensional space. If you take Math 254, linear algebra, they talk about n-dimensional space all the time in that class. Very conceptual. You know, at higher levels of math, they go on to n-dimensional space. You can talk about it. It's just that you can't graph stuff in it. But if you notice from level, let's go back to level curves. Here, you start with a surface that's in 3D that you can graph. That would be this hemisphere. And when you look at its level curves, the level curves are in 2 dimensions. So you drop down a dimension. So the same kind of thing applies here. And what I mean is, even though you cannot graph the function of 3 variables because you would need 4 dimensions, when you set the function equal to a constant, you drop down a level. You drop down into the 3D world. That's why we can talk about level surfaces of functions of 3 variables. So your step 1 is going to be set your function equal to a constant again and try to figure out what it is you're looking at. So here, step 1, if I set this function of 3 variables, which you can't graph, equal to a constant, it will give you something you can graph, because that's a surface. So 4x squared plus y squared plus c squared equals some number, some constant. And it turns out that these are ellipsoids. So the level surfaces for that function is ellipsoids. Okay, we'll get more into being able to visualize this, but I just want to say that n-dimensional space, you know, is kind of cool. And I'm just mentioning once again that this function, if you tried to graph it, it would be in 4 dimensions, but you can still talk about level surfaces. And here's sort of an idea of independent variables. So this is a nice definition. If you had a function like this with all the variables that it has in its you know, domain there, x1, x2, all the way up to x sub n, then it would assign some real number to that function. That's the idea. The domain is n-dimensional space, and the range is in n+1 dimensional space. So they're just giving you, here's your number of independent variables, here's the notation you would use for explicit form. Implicit form is where you get everything on one side and 0 on the other. Now, I don't know if you remember from Calc 1, but if you had something like y equals x squared and you rewrote it, where let's say you subtracted y from both sides, this is still the equation, but it's what we call fxy equals 0. So this stuff on the left-hand side, right here, that is now a function of 2 variables that you're setting equal to 0. And you could do the same thing for all these others, where if you have a function of 2 variables, if you move everything to one side and 0 on the other, here's an example. And by the way, the reason why I'm doing this is not to bore you to tears. You are going to be doing this, having to get your explicit form equation into what's known as implicit form. And if you fail to do that, and this is coming up in this chapter, oh my God, you will just get the problem completely wrong, and I give 0 partial credit. I have no mercy, because you missed the boat. So let's say you had, I'm just going to make something up, z equals, let's do a paraboloid, because those are fun. Let's say, hey, there's explicit form. It's a paraboloid. You can even graph it. It looks kind of cute. Fine. If you move everything to one side and 0 on the other, and it doesn't matter what side you move the crap onto, just pick a side. This is now a function, we'll call it big F, of 3 variables. And you're setting it equal to a constant, and the constant happens to be 0. So this is the format of a level surface that we just got done studying 5 seconds ago. Okay, so that's level surfaces, and you know, if you have any math problems, you know, call somebody who cares, right? Okay, so I'm going to pause there because we're officially done with this section, the first section of your multivariable module. Okay. Questions? You want me to scroll back up?
Does Z turn into a T?
Does the Z turn into
Yeah, like when you were demonstrating how to rewrite it into implicit form at the bottom of the
yeah, it
page.
stays a Z. That
Oh,
should
okay.
be a Z, and my handwriting is pretty bad. It doesn't turn into any other thing. So I apologize if that looked like he magically turned into a different letter. He's still a Z. And that's because this right-hand side is a function of 3 variables now, x, y, and z. And this is called the more general representation that we're going to need later on at the very end of this chapter when we start finding tangent planes to surfaces. Similar to finding equations of tangent lines that you did in Calc 1. So like just to let you know where we're headed for all of you, like, oh man, I can't believe what we're doing. We're going to do a lot more in between now and then till the end of the chapter. But do you recall in Calc 1, if somebody gave you the graph, say of y equals f of x, and they picked a point, like, oh, there's a point, hey, and then they drew a tangent line to that point, and then they said, hey, go get the equation of that tangent line. Do you remember that?
Yes.
Do you remember doing that like 50 million times?
Yes.
I sure hope so. So what is the equivalent here that I want you to not lose sight of in this class? I'm trying to get you to sort of think ahead here because it'll actually help your understanding if you have an idea of there's a light at the end of the tunnel to all this. You're going to have some funky surface. Let me just make some capping surface. This could be some mountain, mountaintop or something. And it's basically the graph of a function of two variables. There he is, beautiful surface, all right? I'm going to pick a point on the surface, okay? I don't know, hell, I'm just going to pick any old point here. Hey, how about right there? Hey, there's a point on the surface, cool. And instead of drawing a tangent line to that point, I'm going to draw a tangent plane. Ooh. That is a tangent plane to the surface at a point. And we'll call it point P if you like. That point right there is the point P. Okay? And here's where a lot of your knowledge is going to come into play. I want you to get that you've been in this class for a month and you actually know a lot. Even if you did crappy on the midterm, you still got a chance to do well if you really got some stuff for yourself. And one of those things is, you guys know how to find the equation of a plane, or what that requires.
It's the normal vector
Good.
and
And
a point on the plane.
beautiful. Those are the two ingredients. So the good news is they'll give you a point on the plane because it's also on the surface. Your job is going to be, how the heck do I get that normal vector n? So I'm not going to tell you yet, because it's, you got to come to this class. But within about 2 or 3 weeks, you'll know how to do it. You'll be good. So that's where we're headed, among other things. Okay, so keep your eye on the ball for that as we keep plowing through the multivariable portion of this course. Okay, so I'm going to put a save on this, and we're going to move on to the next section. So we're done with 15.1. Congratulations, you just finished your first multivariable calculus section. Let's get out of here, close it, and let's go into the next section. So the next section is really cool. I like it because you're going to look at limits. Oh yeah, we're going to do some limits. Oh, but we already did limits for vector valued functions. I'm done. I don't want to do any more limits. I've had it. Well, news at 11, limits aren't going to go away because that's part of calculus. You'll see all kinds of limits. It never goes away. I mean, basically, calculus is limits. I mean, where do you get the definition of a derivative? You take the limit of a difference quotient. How do you get an integral? You take the limit of a Riemann sum. Everything's about limits. There's no getting away from it. It's all limits. Okay, so we're going to look at this definition of a neighborhood. We're not talking about Mr. Rogers' neighborhood, for those of you that even saw Mr. Rogers. I grew up with Mr. Rogers. And then we'll do the limit of a function of two variables. And then we'll do some examples of finding limits. We'll do a couple the hard way and then some the easier way. But the easier way is going to involve algebra, so just so you know. And then we'll look finally at continuity. So I don't know how much this section I'll get through today. I'll get through as much as I can. And then we're going, and I might even have you try something. We'll see how good you are at factoring polynomials. So in this section, just to tee it up, the good news is, even though I'm going to go over the technical definition of a limit, which involves epsilon delta, unlike your Calculus 1 course, I won't have you actually find a limit using the epsilon delta definition, because it's kind of a hassle. Although some teachers might make you do it. I don't know. So I'll do that. And then we'll find limits basically doing just by, for the most part, doing brute force. And a lot of the brute force requires algebra. So some of the algebra that's going to be required, so you don't get too freaked out when it hits, is you have to know how to rationalize either numerators or denominators with more than one variable. And we'll go over it. So that's one. The other thing you have to do is you have to be able to factor trinomials of two variables. And you learn this in a beginning algebra class. And how do I know this? Because I've taught beginning algebra many, many times. And what I find is when people get to Calc 3, they forgot how to factor polynomials. And I'm going to put these on quizzes and exams. Like, it's a big deal for me. Our book doesn't have as many, but I've created some in my math lab. because I did some custom made MyMathLab problems in the summertime. It involves a little bit of code. For those of you who are interested, that's where my code skills pay off. All right, let's do a Calc 1 review. In Calc 1, you learned that if a limit of f of x is equal to L as x approaches some number c, the official definition is the following. It means that for every epsilon greater than 0, epsilon is usually some very small positive number like 0.01 typically, there's a corresponding delta, also a small positive number, such that as long as the x is within the close distance of the number c, so the way they do distance in mathematics is they take the difference and then they take the absolute value. That just means the distance between x and c is less than delta, so that means it's small. So the distance between these guys is small. So you're taking a limit and x gets closer and closer and closer to the c. As long as that's happening, your f of x is very, very close to your limit. So this distance between f of x and L is very, very tiny because epsilon is also a tiny number. That's all they were saying when you took a Calc 1 class. But it's the official way to say it. Because in mathematics, you can't go, oh, when x gets really close to c, then f of x gets really close to the limit L. Because really is not technical. But that's essentially what this definition says. And then they draw a little picture here, you know, when here's your c, and when you're in a neighborhood here, c plus delta, c minus delta. So if as long as you stay in a small neighborhood up here, you're really close to your limit, your corresponding x will be close to your number c. So this is what they're saying in English, and so we have to do an analogous version of it here in 3D. So how do we do it? And there are some similarities and there's some differences, so we'll go over both. So first up, let's talk about some of the notation, which is sort of similar. You're going to still use the word lim. That's similar. Instead of f of x, you're going to have your function of two variables, so f of x, y, and hopefully it'll have a limit existing, so you'll have it equal to L. But down here, this is different. Instead of x arrow c, you're going to have the point x, y gets closer and closer and closer, that's the arrow there, to a fixed point x naught, y naught. So the x naught, y naught is the fixed point that you're trying to get very close to. Okay, and if the limit exists, then you're there. All right, keep in mind that this limit is basically the z coordinate that gets hit, if there is one, which is analogous to when you did it in Calc 1, and I don't know if you remember this because I don't know where you came from with your Calc 1 class. When you did this L, this is the y coordinate that gets hit. If the limit exists. So here we're doing a z coordinate that gets hit, the altitude. Okay, so we're still going to use absolute value notation. When f is really close to L, it's going to look like, and this is how mathematicians do distances, they take a difference, so the difference between f, x, y, and L, and then they put absolute value bars on there to ensure that it's a positive result because your distances, well, you don't want your distances to be negative, could be 0. So it could be as long as it's non-negative. Less than epsilon, where epsilon is something small. Typically like, you know, 0.01 or 0.001 or maybe 0.00001, something tiny. So now here's a key difference for us in Calc 3. Okay, this is a key difference. In Calc 1, you were dealing with intervals because x got really close to c over here on the x-axis. But we don't have an x-axis as our domain. The elements of our domain don't live on the x-axis. They live in the xy plane. So you don't have this idea of an interval. There's no such thing. Instead, the 2D analog of an interval is known as a delta neighborhood. I'm not making this up, folks. And it's a neighborhood close to your fixed point. So here's a picture. Your fixed point is right there. and then you pick some small number delta that's going to be a radius essentially of a disk. So the delta neighborhood is basically a disk centered at your fixed point with that tiny radius. So you can actually describe the disk using set notation. And here's where set notation is used to describe a region in a coordinate plane. So you're going to have these curly braces here, and you're going to go all the ordered pairs x, y. This is ordered pair notation here, ordered pairs x comma y, such that, and then here you're basically just going to describe this circle. So let me just set it up here. If you were going to do the circle standard equation for a circle that you learned in a pre-calc class, it would look like this, right? But we want the points that are strictly inside the circle, and then if you square root both sides, you'll get what I'm going to say, which is the square root of, we're doing the distance formula here between the arbitrary point xy, which is somewhere here in your disk, and you just want to stay really, really close to the fixed point. That's all they're saying. That's just a fancy schmancy way of saying, hey, stay inside your disk. Stay inside your delta neighborhood, people. Okay, if you have a strictly less than symbol like we do here, the disk is called open. You've heard of an open interval. An open interval does not include its endpoints. Well, an open disk does not include its border. That's why you see a dotted line here. So you'll see a dotted line if they're drawing an open region there. If it had a less than or equal to symbol, then just like a closed interval contains its endpoints, then the disk would be closed. Here's some more definitions I don't want to spend too much time on, but mathematicians spend a lot of time on it. And it's kind of obvious from my picture. If we have an interior point in a region, that means you can find a delta neighborhood around that point that stays strictly inside the region. On the other hand, a boundary point is not an interior point, because if you put a little disk around the boundary point, part of your disk goes outside your region, which is not good. You don't want to go outside the region, so that's bad typically. So if the region contains its boundary points, we say it's closed, just like we did. So that's nice. All right, let's keep going. Now let's have you do the official definition, just so you can say you saw it, and that way I'll feel better. So this is the official epsilon delta definition of a limit for a function of two variables. Great, there it is. Let f be a function of two variables defined except possibly at your fixed point on an open disk centered at your fixed point, x naught, y naught, let L be a real number, then saying that this limit as the point, arbitrary point xy approaches the fixed point, x naught, y naught of fxy equals L, if for every epsilon that's greater than 0, and epsilon is typically a tiny number, there's a corresponding delta that's also positive, usually also a small number, such that the difference between your function and your limit is small whenever you stay in your neighborhood, your delta neighborhood disk. Okay, and here's a picture of it. So you're going to get closer and closer and closer to your x naught, y naught down here, and then from here you're going to get closer and closer to some altitude. So now let's do some actual problems, because good news, I'm never going to have you use this epsilon delta version for the definition to find any limits. Okay, I did want you to see it for your education purposes. So you can at least say, yeah, I saw it. I don't know how to use it, but I saw it. And I'm actually going to do a problem where I do use it, just so you can see it in use. And this is mostly for my math majors, because when you take math higher levels, you do proofs. Well, if you don't like proofs, then be an engineer. That's why I became an engineer my first try, because I like solving problems. Using my math knowledge to solve problems. Another good major, if you're a mathematics person who likes solving problems, is major in computer science. A lot of money in computer science. Okay, first up, example 1. Evaluate this limit. Just like you found limits when you were in a Calculus 1 or Calculus 2 class, use direct substitution. That's always step 1. So what am I going to substitute? Where they're saying the point xy approaches the point 1, 2. Just substitute. Substitute what? What do you think?
X1.
What am I going to substitute in place of x's? I'll open it up for chat.
1.
How did you know that?
I just looked at the orientation or the order.
Yeah, the order, yeah, the x coordinate looks like it's going to be 1. So I'll have 5 times 1 squared, and then what am I going to, times, what am I going to put in for the y?
2.
2. So you're going to have 1 squared plus 2 squared. So this is going to look like 10 over 5. Okay, and we get an actual value, so we're done. So the limit exists, and it's 2. Will I give you problems that are that easy? Nope. I just put that in there to boost your self-esteem. Now let's do problems that are much harder. So this next one, I'm actually going to do sort of this epsilon delta proof because I can. So before I do it, I'm going to do some prep work. First off, if I did use direct substitution, I hope you notice I get 0 over 0, which is not 0. It's what we call indeterminate. Who knows what that is? Now, you cannot use L'Hopital's when you have functions of 2 or more variables, although some people might argue you can, and there's some weird stuff out there, but if I catch you doing it, you're dead. There's one time where I'll make an exception, and I will do an example of that in this section, and I think my math lab has a problem like that where they let you make one exception, but you're really not doing it on a function of 2 variables. You're using, you're rewriting it as a product of functions of single variables, and then you can use L'Hopital's, okay? So your L'Hopital's is not going to really help you. So then what? Well, so then you got to, oh man. So in this particular problem, because I can't factor and reduce it, because it's pretty much simplified as far as it'll simplify, I'm going to do some prep work. And the prep work, I need you to buy a couple of facts. So I need you to accept these 2 facts. And they're pretty obvious facts. So hopefully you won't have too much of a problem going, yeah, I'll buy it. So fact number 1 is something that you hopefully learned in a pre-calc class, that if you take the square root of something squared, it's equal to the absolute value of that variable. That's true. And then further, I'm going to embellish this fact, that is less than or equal to the square root of x squared plus y squared. Do you buy that?
Yes.
So hopefully, like, look at the far left. Wouldn't you agree that the square root of y squared is definitely going to be less than the square root of, if you add something underneath that radical to your y squared? Of course, that's going to be less, you know, or equal. If x is 0, then they're equal. The second fact that I'm hoping you'll buy, and then we're ready to do this, is if you had some positive number like x squared, and you divide it by the same number, x squared, plus some extra positive stuff, this is going to be a fraction that's less than or equal to 1, depending on what y is, right? So hopefully you buy these 2 facts, and if you do buy these, then you're going to be fine getting to the rest of this problem. So it's not that hard, but it's sort of the general idea is this is how a math proof goes. So then in a delta neighborhood, that's a fancy phrase for disk about the fixed point, and the fixed point that we're using is this right here, the 0, 0. That's what we're trying to approach. You have this inequality true. You have the square root of, and this is where you do the distance formula between an arbitrary point x, y, and your fixed point, 0, 0. That's going to be less than delta. And so for your arbitrary point, not exactly sitting on top of your fixed point, so maybe it's just getting real close, you would have, you want to examine something, I don't know what, the difference between, that's weird, the difference between fxy and your limit. And we're going to guess, we're going to take an educated guess. We're going to guess that L is equal to 0. It may not be, but if we can get a corresponding delta for epsilon, we're good. So what we're trying to do here is we're going to go, we think this, and what was our original function? Well, you go up here, this right here is your original function that you're trying to find the limit of. Okay, so let me copy him down. What the heck? That was 5x squared y all over x squared plus y squared, minus 0, so it's basically that. And so now we're going to look at this. So minus 0 doesn't mean anything, so let me just rewrite it without the minus 0. This is where I'm going to start using some of these handy facts. First up, I'm allowed to pull a constant multiple out of an absolute value. So the absolute value of 5 is just 5. And then I'm also at the same time, just because I can, I'm going to pull this y out, and you can't say it's equal to y. You still want to make sure it's a positive result, so that. And then what's still left inside my original absolute value bars? I got that. Now what? Well, remember I had you buy that this guy is less than or equal to what? What is one of the facts I asked you to buy?
Less than or equal to 1.
Very good. So this is going to be less than or equal to 5 absolute value times 1. But then this is less than or equal to 5 times, what is absolute value of y less than? That right there. So you replace this, but then this is your delta. This is strictly less than, if you look at what we said, this disk neighborhood, he's less than delta. And you're almost done here. So you're going to go strictly less than 5 delta. And then the rest of the proof looks like this. This is where the mathematicians come in. Hey, if we choose epsilon to equal 5 delta, so we'll go, hey, you know, delta is equal to epsilon over 5, then we can conclude that the limit as xy approaches the point 0, 0 of this function, 5x squared y all over x squared plus y squared, does in fact equal 0. And I'm done. So there is a problem where they actually use this whole epsilon delta definition, and it's, as you can see, it's pretty hairy. It's got a lot of tricks to it. Like, where did they get these tricks and how did they know? Yeah, good question. And sometimes when you take one of these upper division math classes, you'll see a lot of the proofs are just tricks, and you're like, man, I suck at tricks. Okay, so now let's do some ones that are easier, that you don't have to do any epsilons or deltas. Okay, take a look at this baby. Let's use some of the limit facts that I gave you from like 3 weeks ago when we did vector valued functions and limits. If you use direct substitution, you get that. But what did I say that was equal to? Does anybody remember the limit facts?
Infinity.
Very good. And you're done, which is also D and E because it doesn't exist. If you graph this surface, I just want you to see what this would look like in 3D. It's kind of cool. It kind of looks like a volcano. So as you get closer and closer to the point 0, 0 down here in the XY plane, because this thing keeps blowing up forever and ever, you know, it keeps going up, 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 up. I hope you can see that the altitude essentially is infinity. You basically have an asymptote there. Okay, how about this one? This is e to the negative 1 over 0, but that's e to the negative infinity, which is?
0.
0. Very good. And that's the answer for number 4, example 4. Okay, here we have an arctan, and so if we use direct substitution, we have arctan of what? What's 1 over 0?
Infinity.
Yeah,
which
then
is
what's the arctan of infinity?
pi halves.
You're done. That's the answer to example 5. Okay, we're moving. Now, do you remember in Calc 1 that they taught you that sine theta over theta as theta goes to 0 is what? Let's do it in slow motion. Okay, sine of 0 over 0. Oh, damn, it's 0 over 0. Didn't we use L'Hopital's?
Oh, wait, I remember now.
So we can take the theta going to 0 limit again. What's the derivative of sine theta?
Cosine theta.
Cosine
Okay.
theta.
And you're going to divide that by the derivative of theta, which is?
1.
Good. And now use direct substitution. What's cosine 0?
1.
1.
That's the answer. So here's the theorem that they taught you in Calc 1 because you weren't allowed to use L'Hopital's. They said, hey, kids, just memorize the fact that if you're taking a limit as theta goes to 0 of this quotient, sine theta over theta, or the reciprocal, same thing, theta over sine theta, the answer is going to be 1. Yay! So how is that going to help us here in Calc 3? I'm going to show you. If somebody asks you for this limit, where you can think of x plus y as substituting in for your theta, here you have theta over sine theta, and theta is going to 0 because x and y are both going to 0, so of course x plus y. 0 plus 0. There's your theta going to 0. Your answer, you know, if you just use direct substitution, you're going to go, oh, I get indeterminate, go use L'Hopital's. But you can't use L'Hopital's on functions of two variables. But you're going to use your knowledge from Calc 1 that this has that flavor of sine theta over theta, or theta over sine theta, where the theta is the x plus y. And so your answer by the theorem is going to be a 1. Okay? So on your handwritten work, if you use this one, I want you to say by the theorem, and you want to quote this theorem and write it down so I know that you know that you know that I know that you're, you know, not just pulling it out of the air. So you can use that whenever it's helpful. Okay, and let's see, example 7. So here's the key fact. Don't use L'Hopital's, except here's the exception. Example 7 is my exception. So when can you use L'Hopital's? When you're trying to find limits of functions of more than one variable. If you can rewrite the function as a product of single variable expressions, then you can individually apply L'Hopital's on any of those functions of a single variable, factors, if you will, that will work for you. Okay? So let's take a look at this example. First, use direct substitution. We're trying to approach the point 2, 0. So if I use direct substitution, I'm going to go 1 minus cosine y, but y is 0, divided by 5 times x is 2, times 0 squared. Well, this looks like 1 minus 1 over 0. Oh, dang, I get 0 over 0. Now what? That's a function of two variables. You can't use L'Hopital's. But here's the trick about this problem. You can't always do that. Would you agree that this expression is equivalent to, be careful here, this product?
Yes.
Yes, it is. And I want you to notice, as you're taking this limit, as xy approaches the point 2, 0 over here, this right here, this first factor, is a function of a single variable. It's a function of y only. So then it's legal to use L'Hopital's on that if you need to. And this other factor is a function of a single variable, just x only. Yay! And if you need to, you can use L'Hopital's on that. Turns out this guy, you don't need L'Hopital's, because when you plug in x equals 2, this factor is going to be 1 divided by 5 times 2, or 1/10. Okay, so that's pretty easy. But what about this other factor? Well, that's where you're going to end up with 1 minus cos 0 over 0 squared, and you get this 0 over 0 indeterminate. And then you use L'Hopital's on just this quotient here. So you go, okay, I'm going to take the limit as y goes to 0, and you take the derivative of the numerator. Let's see, the derivative of 1 minus cos is what?
Sine of y.
Sine of y.
Y.
And then you divide by the derivative of y squared. I think that's 2y. And you're like, oh no, I'm going to get another one of these 0 over 0. Oh shoot, now what? Oh, you can use L'Hopital's again, fine. So you're still going to take the limit as y goes to 0. The derivative of sine y is what? Cos y. And divide by the derivative of 2y, that's a 2. And then cos of 0 over 2 is 1/2, isn't it? So your final answer is you're going to take the product of these two limits that you got for functions of single variables, and your answer will be 1/20th for this guy, okay? So that guy does have a limit. It looked like it didn't at first, but it does, so you're good, okay? So that is the one time I'm going to be like totally okay with you using L'Hopital's if you need to. I think this is a good place to quit. Just to let you know, the algebra that I mentioned at the beginning of this lecture, we didn't use too much of it really. It's going to happen with example 8 and 9 and 10. So that's where it's going to come into play. And then we'll go over how to show a limit does not exist, which is actually easy, although some students make it hard. And that will wrap up section. Oh, we're going to do polar coordinates limits. Ooh, those are fun. Love those. And if you recall, we did polar in Calc 2, like the last week of class. Then we'll do continuity, and then we'll be done with this section. I may start the partials a little bit Friday if I have time. And then, as I mentioned, Monday is going to be no class because of the Jewish holiday. And then you'll watch the rest of the partial derivative stuff through my videos. Okay? So I'm done. I'll stick around if you want to, like 5 minutes before I hit my next class. You're welcome to stay.